Imagine two identical clocks. You leave one at sea level. You carry the other up a mountain. Nothing looks different. Both clocks have the same battery, same mechanism, same starting time. But when you bring them back together, they don't quite agree. One has experienced slightly more time than the other. And this isn't a malfunction. Time itself has actually passed at different rates. It sounds like science fiction, but it's one of the strangest predictions of Einstein's relativity, and scientists can measure it with extraordinary precision. NIST. The reason begins with something we normally think has nothing to do with clocks. Gravity. According to Einstein's general theory of relativity, the stronger the gravitational field, the more slowly time passes. That means the closer you are to Earth's center, the slower your clock ticks. And the farther you climb away from Earth's center, the faster it ticks. The difference is unbelievably small, but it is real. In fact, scientists have measured it with clocks separated by less than a meter. In one experiment, researchers at the National Institute of Standards and Technology compared two extremely precise atomic clocks positioned about 33 centimeters apart. The clock just 1 foot higher ticked slightly faster. That means, in a very literal sense, you age faster when you're standing on the upper floor of a building than when you're standing in the basement. NIST. Of course, you would never feel it. The difference is far too tiny for a human to notice. But atomic clocks can. And these aren't ordinary clocks. An atomic clock doesn't simply count the movement of gears or the swinging of a pendulum. It measures incredibly precise frequencies associated with atoms. The best modern optical clocks are so precise that they can detect changes in time caused by extremely tiny differences in gravitational potential. NIST, and here's where things get even stranger. Scientists eventually pushed this experiment down to a scale almost impossible to imagine. In 2022, researchers measured gravitational time dilation between two parts of the same cloud of atoms separated vertically by about 1 millimeter. That's roughly the thickness of a pencil tip. Two regions separated by that tiny distance were, effectively, experiencing slightly different rates of time. NIST. But mountains make the effect easier to understand. Take Mount Everest. At the summit, you're farther from Earth's center than someone standing at sea level. Gravity is slightly weaker, so your clock runs slightly faster. You aren't jumping into the future. You're gaining an unimaginably tiny amount of extra time. Over an entire lifetime, the difference is still microscopic. But physics doesn't care whether the difference is convenient for us to notice. If the clocks can measure it, the effect is real. And there's an even bigger example above your head. GPS satellites. Every time you use Google Maps, order a ride, or share your location, you're relying on satellites carrying incredibly accurate clocks. Those satellites are moving extremely fast, which causes one relativistic effect. Their clocks should run slower than clocks on Earth. But they're also much farther from Earth's gravity, which causes another effect. Their clocks run faster. The two effects work in opposite directions. And when scientists add them together, the satellite clocks end up running about 38 microseconds faster every day than clocks on Earth's surface. NIST. 38 millionths of a second doesn't sound like much. But GPS can't afford to ignore it. If engineers didn't correct for relativity, positioning errors would accumulate rapidly enough to make the system useless for navigation. So every time your phone finds your location, Einstein's theory is quietly working in the background. NASA science assets. And this gives us a bizarre conclusion. There isn't one universal clock ticking at exactly the same rate everywhere in the universe. There is no cosmic stopwatch sitting above Earth saying, "This is the exact time for everyone." Your time depends partly on where you are, and partly on how fast you're moving. Move faster and time slows down relative to another observer. Enter a stronger gravitational field, and time slows down again. Near an extremely massive object, the effect becomes dramatically stronger. And that's where the story leaves Earth. Imagine traveling toward a black hole. As you approach it, gravity becomes enormously intense. From your perspective, your own clock continues to tick normally. Your heartbeat feels normal. Your thoughts feel normal. But someone watching you from far away would see your clock behaving differently because of the extreme gravitational environment. The closer you get to the black hole, the more dramatic the difference becomes. This is why the phrase time is relative isn't just a philosophical expression. It is physics. And the strangest part is that we don't need a spaceship or a black hole to prove it. We can demonstrate it with two clocks, one on the ground and one slightly higher. We can measure it across mountains. We can measure it with satellites. We can even measure it across a distance smaller than your finger. So the next time you climb a staircase, remember something strange. You haven't just changed your location. You've entered a slightly different gravitational environment. And somewhere inside your body, every second is passing at a rate that is microscopically different from the person standing one floor below you. Time isn't a universal river flowing at exactly the same speed everywhere. It bends with motion. It responds to gravity. And even here on Earth, there are places where time literally runs differently.